Hello everyone. So I thought it would be a good idea to go through sample problem 2.7 together. This is from the normal tangential section, and it's a really comprehensive and complete problem for this section. If you can't find it under 2.7, it might be different number for your edition of the book, but it was 2.7 in the 7th and the 9th edition, so I imagine it should be the same for you as well. So let's read the problem statement. I've already highlighted some important information from it. So there's a car going through a dip and a hump in the road, and the driver applies the brake to produce a uniform deceleration. Uniform, I've highlighted that. And the speed at point A is given at this point. That's 100 kilometers per hour. And we also know the speed at this top of the hump. That's 50 kilometers per hour. And there's a distance of 120 meters between these two. And this distance is actually divided into two parts. From A to the inflection point, there's 60 meters, and from the inflection point B to C, there's another 60 meters. If we know the total acceleration, let me highlight that. So this is total acceleration of the car at A. And if you know the radius of the curvature at C, then calculate the radius of curvature rho at A. So this point A has a curvature, so it has a radius. Let's say it looks like this, rho A. It also wants to know the acceleration at points B and C. So let's write down what we're given. What we're given is uniform deceleration of the car. So what is that deceleration? What's the symbol? So I talked about this. When you're in a car and the car is when you apply the brakes or the gas pedal of the car, you're inputting acceleration and deceleration along the path, right? Because the car is moving on the path. It's moving tangential to the path, basically. So this is AT, this deceleration that is talking about. Uniform deceleration is uniform AT. And that means that it's constant from A to C. Throughout this whole process, going from A to C, it has the same constant value. We also know VA, and we also know VC. We know the distances between S. So let's call this, let's assume that at A, SA is 0, so we know SB is 60 meters, and we know SC, that's 120 meters. And finally, we know rho C. And we want to find rho A, AB, and AC. Okay? So first thing that we should do to make our lives easier is convert speeds to meters per second so that we can work with the accelerations. So VA is given 100 kilometers per hour. If you don't remember how to convert this, so you need to multiply it by two things. First, remember that 1 kilometer has 1,000 meters in it, and 1 hour has 3,600 seconds. So this is the same as just dividing that number by 3.6, and that gives us a speed of 27.8 meters per second. Let's do the same thing at C. It's given 50 kilometers per hour, so it's going to be just half the value we found, roughly 13.89 meters per second. Okay, so that's the first thing. Second thing that we need to know before we start is that we know VA, we know VC, right? We know the speeds at the beginning, at the end, and we know the AT along this path is a constant. So that means that we can find AT, right? And why is that? Because in this curvilinear motion, you have AN and AT. But if you only look at the AT, if you're only looking at the motion along the trajectory, tangential to the trajectory, then you can treat it as like a rectilinear motion, right? You can think of, let's say you have this path and you're going to be moving along this path. It's going to be the same as if you just make this completely flat. There is, of course, other components to the acceleration, the normal ones. But if you're just dealing with AT, and the speeds are only tangential to the path, so speeds are really, we only call it v, but it's just vt, right? There's no vn. So if you're just dealing with that AT and that speed vt, or v, as we call it here, then you can just use our equations from rectilinear motion. Did we have an equation that would help us find? So if we know the speed at 2 points and we know the distance between them, can we find the acceleration? If you look at the formula sheet for the exam, then v squared of the end point minus v squared of the initial point is 2 times acceleration, which is AT in this case, is c minus sa. Okay, so let's plug in those numbers. So let's write AT in terms of v and c is going to be half of vc squared, va squared, divided by sc minus sa, right? We know those numbers, so we get a value for AT. So VC was, VA is 27.8. SC minus SA, that's 120 meters. So finally, we get an acceleration of minus 2.41 meters per second squared. And it's a negative because, as the problem statement said, it is decelerating, right? So that makes sense. Okay. So remember that this is AT. So we found AT. So now let's go through each part individually. So part A, what is it looking for? So it's asking us to find the radius of curvature at A. So the radius at curvature shows up in AN, right? We know what A is, total A. So that's given here, it's given here is 3 meters per second squared. So we know that at A, total acceleration is 3. We just found from the previous step that AT is also given. AT is constant throughout the process, so it's the same at A and other points. So we can easily find an, because a is at squared plus an squared. So an is an squared is a squared minus at squared. So at a, we can find an squared is 9 minus 2.41 squared. Let me write this as 3 squared. And if we solve this, then an is going to be 1.785 meter per second squared. Okay? And we know that an is v squared over rho. So rho at a is, this is at a, right? So rho at a is v at a squared divided by an at a. And the v we found it up here. It's 27.78. an, we just found that to be 1785. And that number ends up being 432, and it's meters, right? Because it's a radius. Let me put a big box around this. Okay. Oops. Okay. So that's part A. That's what it was asking us. Now let's do part B. What is part B? Part B is asking us to find the acceleration at the inflection point. So this is interesting. So at the inflection point, if you remember what an inflection point means, that's a flat surface. At that point, at inflection point, there is no curvature, right? That's the point where curvature goes from some sign, some negative or positive, to 0 and then to the other sign. So at that point it's 0. So if you remember, we mentioned in class that for a flat surface at like an inflection point, rho is infinite. Or in other words, you can also check this, so maybe you can do this on your own. Check if this is true from equation of rho given in the homework. So in one of your homework problems, I gave you the equation of how to find rho as a function of, if you're given the function of y and x. So if you remember what an inflection point is, then you should see that the rho is going to be infinity at that point. Okay? So at the inflection point, it's like a flat surface. You don't have any an. So an is 0. That means that your total acceleration is the same as the tangential acceleration, which we know what it is. It's constant, right? It's minus 2.41 meters per second squared. Is constant from A to C. So that was the easiest one. Let's put a box around this as well. You only need to, it's asking for A, which is AT. But I'm also putting a box around AN because it's important to know why it's 0. Finally, part C. What is part C asking for? let's go back. Part C is asking for total acceleration at point C. At point C, we have a curvature, so we're going to have both AN and AT. So at C, let's write it down. So AT is what we have already found. AT, we already know it's minus 2.41. That's not a problem. How about the other one, AN? AN at any point, the curvature is v squared over rho. V is given up here. It was 50 kilometers per hour, and we turn it into meters per second. It's 13.89 squared divided by the rho, which is given in the problem statement. It's 150 meters. And 50. So this turns out to be 1.286 meters per second squared. Okay, so we're almost done. Now we just need to find, we know ATAN, we need to know the total magnitude, which is minus 2.41 squared plus 1.28 squared. And that is 2.73 meters. Let me write it down there so there's enough space. So basically A at C is 2.73 meters per second squared. And let's put this in a box. Also, let me go back to part B and just write down that this was AB. And yeah, so that's how you would solve a problem like 2-7. It's a really good example, so definitely try to do it on your own again. And let me know if you have any question, if anything was unclear. See you next week.